My title is State-Driven Influential Nodes Identification in Dynamic Social Networks. This paper studies the influential nodes in social networks. Now let me introduce some definitions. With the development of the mobile internet, the online social network plays a vital role in information dissemination among a vast number of users. The social network can be abstractly regarded as a network topology model composed of nodes and edges, which can reflect the social relations among social individuals. Compared with other nodes, influential nodes in social networks are more likely to affect the state of nearby nodes, which makes the information spread more widely. The research on influential nodes has wide applications. If we identify influential nodes quickly and accurately, it will be better for the government to achieve the guidance and control of major public feelings affairs. For business, influential nodes identification applied to precision marketing will effectively improve merchant marketing efficiency and reduce promotional costs. However, influential nodes identification models perform unsatisfactorily in complex network. First, existing models only focus on the metrics related to the network structure without considering the dynamic propagation characteristics of the network. Second, existing models do not maximize the integration of multiple metrics that reflect various aspects of node characteristics. Some design models assign the same weight to the input metrics, which is unreasonable. Third, the selection of indicators for the design model lacks theoretical support and ignores the logical derivation process. Considering the dynamic propagation characteristics of real-world social networks, we establish a data-driven influential nodes identification model, which mainly contains two models: multi-scale comprehensive metric system and data-driven metric weight optimization algorithm. In order to deal with the inaccurate quantification of nodes influence in previous models, we establish a multi-scale metric system as shown in this figure. The metric system consists of three metrics. The first metric is the topic level influence measurement based on user behavior. In social networks, users are influenced by the content of information from the source users, and users also influence the spread of information from the source users. Then we can calculate the influence of the users through mining the behavioral characteristics of users. The dissemination of information between users is mainly affected by two factors. The first factor is the user's interest in this information, which varies with users and information. Therefore, it is necessary to model the user's topics and the content of information spread among users. LDA is used to obtain the topic distribution vectors of users and information. According to the distribution vectors, the probability of the user responding to other users will be calculated. The second factor is the interaction level between users. If user V often follows blogs published by user U, it indicates that the interaction level between user U and user V is high, and user V is likely to continue forwarding blogs published by user U in the future. These two factors are critical in calculating topic level influence based on user behavior. The influence of user U is denoted by BRU. The second metric is influence measurement based on local network structure. For each node in the network, the influence of the node can be measured by calculating the influence of its neighbor nodes. The higher the influence of its neighbor nodes is, the higher the influence of the node is. The third metric is influence measurement based on global network structure. Beginner's centrality can be used to find the nodes that play a key role in the transmission of information. Most of the existing comprehensive evaluation models use uniform distribution or entropy weight method to assign weight to each metric. Uniform distribution ignores the differences among indicators, which is not in line with the actual situation. The entropy weight method uses the information entropy of indicators to determine the weight, ignoring the prior knowledge of ground truth. Therefore, we propose a data-driven metric weight optimization algorithm as shown in this figure. Based on the weights obtained by the entropy weight method, we add the prior knowledge of ground truth to optimize the metric weights. The influence of nodes can be evaluated more accurately with the weighted hypothesis algorithm. In this algorithm, we choose a method to optimize each indicator's weight. After choosing all the ground truths and updating the weight, the results are the optimized metric weights. The metric weights optimized in this way learn the prior knowledge of ground truths and can be used for comprehensive evaluation more reasonably. The data-driven evaluation metric weight optimization algorithm proposed here is a metric weight optimization method that is not only applicable to node influence evaluation models, but can also be extended to other comprehensive evaluation models with multiple metrics. We compare our model with other models on 4 real-world social networks, including email network, Facebook network, Enron network, and Koala network, where nodes denote users and ages denote interactions between users. Several basic statistics are listed in this table. The table contains information about the number of nodes, the number of ages, and the average degree. We compare our models with baselines including entropy-based ranking mirror, W-Watt rank, new evidential centrality, NLPZ, and hypothesis. These methods are comprehensive evaluation models which make full use of the network structure and the information transmitted between users to measure the influence of users. The influence of nodes is sorted, and the top 1% nodes are selected as influential nodes. We use Spearman's rank correlation coefficient to measure the accuracy of influential nodes identification. We use Spearman's rank correlation coefficient to measure the accuracy of influential nodes identification by defined models. Spearman's rank correlation coefficient rho is the correlation between the model results and the simulation results, which is higher when the identification of influential nodes is more accurate. This figure shows that rho changes with the mean value alpha of the influential propagation coefficient, where A2D shows the results of various models on 4 datasets correspondingly. With the increase of alpha, the overall accuracy of the influential nodes identified by defined models tends to increase. As can be seen from this figure, our model outperforms other models generally. In general, if a node is considered as the influential node, it should be able to activate more nodes in the independent cascade model based on the influence propagation coefficient. When alpha equal to 0.2, we plot the relationship between propagation time and the average number of activated nodes, as can be seen from this figure. The influential nodes identified by our model activate the highest average number of nodes after the propagation process reaches a stable state. Obviously, in 4 different networks, the influential nodes identified by our model have the best information dissemination and activation ability. showing higher accuracy than other models. If the number of nodes with the same ranking is small, it proves that the model has good discrimination in measuring the influence of nodes when alpha equal to 0.2. This figure shows the number of nodes with the same ranking in the four networks. As can be seen from this figure, the results of our model have the least number of nodes with the same ranking, while other models have at most 800 nodes with the same ranking. In particular, EIM and AEC have the largest number of nodes with the same ranking. The reason is that each node in a high-density network has a high probability of being in a critical position in the network, which causes the EIM and AEC methods based on the network structure to be effective in ranking nodes. From this perspective, it can be concluded that our model can measure the influence of nodes more effectively. The running time of models is a common index to measure the performance of models when alpha equal to 0.2. This figure depicts the running time required to select the influential nodes using 6 defined models on 4 defined networks. It is obvious that the running time of our model is almost the same as that of the W-Volt rank, and it is more efficient than NEC and NLPC. For small networks such as email and Facebook, it takes no more than 10 seconds for our model to complete the identification of influential nodes. For a Koala network, its running time can also be controlled within 200 seconds. Though our model is slightly less efficient compared with EIM and W-Volt rank, our model shows superiority over them in the accuracy of identifying influential nodes. Therefore, our model has a high time efficiency on the whole. Now, let me draw a conclusion. In this paper, we propose a data-driven model for influential nodes identification in dynamic social networks to make the measurement of nodes' influence reflect the node's real situation in the social network. We mainly focus on 3 aspects, including the quantitative indicators, the metric evaluation system, and the experiment settings. The experiment results verify that our model can achieve better performance on both accuracy and effectiveness. In future research, we will make use of spatial and temporal characteristics of information dissemination in social networks to identify influential nodes. That's all. Thank you for your listening.